Hello dear friends, I welcome you once again to this current video lecture. In the last lecture, we started the spectroscopy technique to study the molecular structure of a molecule. In the last lecture, we studied about the first important analytical technique, that is the first spectroscopy, that is called as the microwave spectroscopy for elucidation of molecular structure. Now today we are going to take the second type of the spectroscopy, that is called as the IR spectroscopy, that is a infrared spectroscopy for the elucidation the of the molecular structure. Now this is the second most important method, spectroscopic method, or it may be called as the one important analytical technique for the study of molecular structure. Now the question arises, what type of electromagnetic radiations can be used in this spectroscopy? So in a electromagnetic spectrum, the region from 10 raised to 3 to the 10 raised to 5 nanometer, the region in a electromagnetic region, that is the 10 raised to 3 to the 10 raised to 5 nanometer, belongs to the IR radiations. So for this spectroscopy, these type of electromagnetic radiations can be used for studying the molecular structure. Now, what type of study can be involved in this type of spectroscopy? Now, in a last spectroscopy, we know that in a microwave spectroscopy, the microwave radiations are used. Whenever that radiations can be absorbed by the molecule, the change can be takes place in terms of the that that molecule gets changed from one rotational energy level to the another rotational energy level. Now in this case, what happens whenever a molecule interacts, whenever a molecule get interact, or when IR radiations can be applied to a particular molecule, then what happens, these radiations again get absorbed by this particular molecule, then there is a change in vibrational motion of molecule can be takes place. Vibrational motion, this vibrational motion of a molecule can be takes place, or we can say that there is a change in vibrational energy level. Vibrational energy level of a molecule can be takes place. There is a change in vibrational energy level of a molecule can be takes place. That's why molecule goes from one vibrational energy level to the another vibrational energy level, and during which what happens, these radiations can be absorbed by the molecule, it get converted from one vibrational energy level to the another, and during such a type of the interaction, what happens, a spectra is obtained, and that spectra is nothing but the IR spectrum or IR spectra. A spectra is obtained, that is nothing but the IR spectra. Now these spectra gives us an information. These spectra gives us an information within a very short time span regarding the functional group of molecule. Regarding the functional group of molecule, this is the first important information we get from this IR spectra. The second thing is that how many bonds or what are the bonds present in a molecule. Bonds in molecule, that information we get from this IR spectra. So these two type of the important information we get from IR spectra of a molecule. First of all, the functional group which is present in the molecule, and second is the bonds present in the molecule can be understand with the help of such a type of the IR spectra. Now what happens, due to such a type of information we get from IR spectra of a molecule, that's why the IR spectrum of a substance, IR spectrum of a substance is called as fingerprint, is called as fingerprint of a substance, fingerprint of a substance or molecule. It is called as fingerprint of a substance or molecule. And why this is so? Because we get an idea regarding the functional group as well as the bonds present in a molecule, and due to which this IR spectra is called as the fingerprint of a substance, means we get an idea regarding the molecular structure of a molecule. So this is an important spectroscopic technique called as the infrared spectroscopy, which is operate within the electromagnetic radiation region of 10 raised to 3 to the 10 raised to 5 nanometer. In this spectroscopy, what happens? Whenever IR radiations can be absorbed by the molecule, there is a change in vibrational motion, or there is a change in vibrational energy level of a molecule can be takes place. Molecule goes from one vibrational energy level to the another, and during such a type of the interaction, what happens? We get a spectra, we get a characteristics absorption bands in a spectra. Then that spectra is called as the IR spectra. From this IR spectra, we get information regarding what type of functional group is present in a molecule as well as the different bonds present in a molecule, and that's why this IR spectrum of a substance is called as the fingerprint of a substance or of a molecule. So this is a simple introduction regarding this IR spectroscopy. Now next important concept after this introduction is vibrational motion of a diatomic molecule. Now what is meant by this vibrational motion of a diatomic molecule? Now just we studied that in a molecule, what happens after the absorption of IR radiation, there is a change in a vibrational motion of a molecule can be takes place. So if we consider a diatomic molecule, if we consider suppose a diatomic molecule, suppose A single bond B, if we consider this diatomic molecule, and if IR radiations can be incident or can be absorbed by this particular molecule, then what happens? So that point we have to study is nothing but the vibrational motion of a diatomic molecule. Now first of all, a diatomic molecule, this diatomic molecule is there, it is considered to be a simple harmonic oscillator. It is considered to be the simple harmonic oscillator. It is considered to be the simple harmonic oscillator, means it show a oscillation at a regular interval, so it is called as the simple harmonic oscillator is there. Now what happens whenever we consider this type of the diatomic molecule, the bond present between these two atoms, behaves as a spring. It behaves as a spring. That bond is not a stationary, it behaves to be as a spring. So what happens whenever we consider this type of a bond as a spring, it oscillates from its equilibrium position. So such a type of behavior can be studied under the three different headings: that bond at a rest, when it is a stretch, and when it is a contracted. So these type of three different cases is there. Now first of all, whenever a bond between the two atoms in a diatomic molecule, if it is present at the rest, then what happens? It has its normal position, or that is called as the equilibrium position of this type of the two that type of the bond present between these two atoms. So this is called as the equilibrium position. This spring has one fixed end. One end is a fix, while second end is a it undergo oscillation. So what happens when this spring undergoes stretching? When this spring undergoes stretching or this bond undergo vibration, what happens? It undergoes some type of the displacement. It undergo some type of the displacement from its equilibrium position, and that's why it has the displacement of x. It has the displacement of this x. So we know that if that spring changes its distance from equilibrium position with the displacement of this x, it want to become again regain its original position, or it want to again attain its original position. We know that this type of displacement, if it want to become again reverts to its original position, it must require some restoring force. It must require some restoring force. It must require some restoring force, and that restoring force is nothing but this F. So this restoring force always act at the opposite direction to that of the displacement. So this F is a anti-parallel to this type of the displacement. Again it converts this original situation of this type of the spring or of a bond between the two atoms in a diatomic molecule. So this is the second situation, stretching. And the third situation is that if a bond between these two atoms get contracted, or if that spring get contracted, then what happens? Again there is a displacement. Again there is a displacement from one end of the spring. Now this displacement is again a value of x. Now again, after contraction, again this spring want to regain its original equilibrium position. So again a restoring force is act again in opposite direction to that of the displacement of the value of f. So we can say that this type of the different three situations can be observed in a bond present between diatomic molecule. So what happens? Due to such a type of the three different situation, a force is involved in these three different situation. That force is called as the restoring force. Now what happens? According to the Hooke's law, according to the Hooke's law, according to the Hooke's law, this restoring force, according to the Hooke's law, this restoring force is directly proportional to the mass which undergo displacement. So whenever such a type of displacement can be takes place, we have to interested to calculate its energy. That energy is called as the vibrational energy. That energy is called as a vibrational energy in joules. That energy is called as a vibrational energy in a joules. So that energy can be given by epsilon, sorry, energy, vibrational energy in a joules is equal to nu plus 1 by 2 h into c omega bar. So this is a simple equation to calculate this type of the vibrational energy of a simple harmonic oscillator. This is a energy, vibrational energy is equal to nu plus 1 upon 1 by 2 into h into c into omega bar. Now in this case, this v stands for the vibrational quantum number. This v is called as the vibrational quantum number, which may have the values of 0, 1, 2, etc. The next term is there, that is the omega bar. This omega bar is nothing but the fundamental vibrational frequency. This is a fundamental vibrational frequency is there. Then this h is called as the Planck's constant. So this is a simple equation to calculate the vibrational energy of a diatomic molecule. That is a simple harmonic oscillator. Now if we want to calculate this energy in a per centimeter, then that is called as the epsilon v in per centimeter. Epsilon v in a per centimeter, then that is equal to v plus 1 by 2 into omega bar. So this is a equation to calculate that vibrational energy of a simple harmonic oscillator in per centimeter is equal to v in plus 1 by 2 into omega bar, where this v is again a vibrational quantum number. This omega bar is called as a fundamental vibrational frequency. By using this particular simple equation, we may calculate the vibrational energy of a diatomic molecule in per centimeter at the different values of this vibrational quantum number. Suppose if you want to calculate energy of a molecule at vibrational quantum number equal to 0, if it is equal to 1, if it is equal to 2, so what type of energy is obtained? So that can be calculated with the help of this type of the simple equation. So this is a simple point from this IR spectroscopy, that is called as the vibrational motion of a diatomic molecule. So this diatomic molecule has these are three different type of the cases. With the help of these three different type of the cases, we may calculate its restoring force, and this restoring force according to the Hooke's law is directly proportional to the mass which undergo displacement. Now when such a type of displacement is there, what is the vibrational energy which is involved? So that energy in a joules can be calculated is equal to v plus 1 by 2 into h into c into omega bar, and that energy can be calculated in per centimeter. That is a epsilon v in per centimeter equal to v plus 1 by 2 into omega bar. So with the help of this equation, we may calculate vibrational energy of a diatomic molecule at the different values of the vibrational quantum number. So in today's lecture, we started the second important spectroscopic technique, that is called as the infrared spectroscopy for the elucidation of the structure of a molecule. So in this lecture, we first of all study the simple introduction regarding the spectroscopy, and in the second part, we completed the vibrational motion of a diatomic molecule. The remaining points from this spectroscopy we will take in a next video lecture. So with this, today I stop here. Thank you so much.